Hey y'all, welcome back to another round of engineering. And yeah, let's keep going. I said last time that I would give you a couple more example problems for operational amplifiers, so I figured, okay, here we go. So queued up for you is another circuit, and we have the description for a plus or minus 5 volt source. So what that's referring to is the op amp power, so a plus 5 volts and a minus 5 volts. So determine the range of sigma. So you notice that we have a sigma right here in the potentiometer that avoids saturation. What is the current when sigma is equal to some fraction? Okay, so we've got a couple of ideas here. Yeah, let's go at it. Now for simplicity, to see if we can get a sense of what's going on with this amplifier, we just stop and ask ourselves if maybe we have some idea about what this thing's going to do. So we notice that the non-inverting input is to ground. And so we expect that whatever comes out, it will be inverted. So we'll probably end up with a potential less than 0. Okay, that's the first thing. The other idea that we have here, let's see. Well, let's go ahead. Oh yeah, the other idea, excuse me. You notice, for example, right here, I'm boxing it. Now, whether this is actually helpful or not remains to be determined, but at least right here, this boxed portion, you notice that you could actually do a source transformation on that. If you really wanted to, rather than considering this potential supply with a resistor, you could model it as a current supply in parallel with that resistor. So you could replace that portion, if you want, with something like this. Okay, so this is the 6.4 kilo ohm resistor. This is the 1.6 kilo ohm resistor. And of course, this source would then become something like 250 millivolts divided by the 1.6 kilo ohms. So you're on the range of microamps. Okay. So you could also run it like that. Now, as I said, I'm not convinced that this is actually going to be beneficial for us. So I probably won't do it that way, but I'm just letting you know that that is perfectly reasonable to do. What the heck? Let's leave it like this. Sure, why not? And then you have, of course, your op amp. You have your variable resistor. You have your 12 kilo ohm resistor, and then your feedback loop. Sure, what the heck? Why not go for it? Take a minute, go ahead, apply some techniques, see if you can come up with the answer. You got it? Good, 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 good. Well, I'll go ahead. Let me, first of all, I'll call this node A. Call that node A. I'll call this one B as in boy. You can see one of the advantages of the source transformation is that you have these drops across the individual resistors now. Okay, so let's go ahead. So of course, golden rule would tell us that the potential at A is equal to 0. Good. It's equal to 0 because the non-inverting input is grounded. Okay. Now, if we consider node A and we want to apply the node voltage, we can go ahead. Notice the current supply is going into A. And so this is one of the rare cases where we would put that negative sign in there. And we have the 250 milli divided by 1.6 K. Okay. Then in addition to that, we would have something like VA over the 1.6 K. We would have VA over the 6.4 K. Okay. And then we would have something like plus, I'll say VA minus VB And these resistors in the feedback loop are in series. So we do something like 12K plus this 50K times sigma. And that whole rigmarole equals 0. Now, of course, now you can see part of the advantage, right? Doing the source transformation and taking into account that the potential of A is 0, we can immediately eliminate those two ideas, those two guys, from our equations. Okay? VA is 0. And so you have a potential drop of 0 across both of these resistors. Remember that this bottom loop is grounded. So the top loop's grounded, the bottom loop's grounded. You have 0 current flowing through those resistors. Cool. All right, how about B, node B? Yeah, you probably already got it. Okay, so we have something like VB over 10K. That's that drop to ground. We have the I going into the output of the op amp. And then we have VB minus VA over that rigmarole again. So we still have that 12 plus 50 kilo ohms, and then times that sigma, that scaling factor. That whole rigmarole equals 0. Sweet. Of course, we could go a little further if we want to. We can go ahead and take out these VAs. I left them in there for right now, but we can take them out and put in zeros and 0. And so we see that this middle equation can be used to find VB in terms of sigma, right? The output potential in terms of sigma. And then, of course, we can use the bottom equation, should we be asked to find the current. So let's go ahead. Let's use that middle equation here. So I've gone ahead and rewritten the equation. And so now we just need to get VB by itself. Sweet. Let's just go at it. I've taken the liberty of writing the kilo and the milli in terms of powers of 10. And so what do we end up with here? We have VB over rigmarole, so the 12K plus the 50K times the sigma equals this negative 250 over 1.6. And then we have something like 10 to the negative 6th. So there's the micro in there. Okay. Which means we have some final equation that tells us VB is equal to negative 250 over 1.6, 10 to the negative 6th times this 12 plus 50 sigma, and I'll go ahead and take that kili and write it as 10 to the 3rd here. And at the end of the day, so we have our 10 to the 6th. We can take 3 of those out. So this is 10 to the negative 3rd. That cancels this guy. Okay. And yeah, I mean, fielder's choice at this point. So I guess we could cancel the other 3 out right here. So we have something that says negative 0.25 over 1.6 times 12 plus 50 sigma. Now we're told that the saturation of the amplifier is plus or minus 5 volts. That's the power supply. We're told that it's an ideal amplifier, so it's okay to use this power supply as the limit. Now in reality, as you're probably well aware, is that the saturation actually occurs slightly below whatever the powering limit is. That's because some of the energy needs to be used to actually operate the op amp. So if you have a 5-volt power supply, your saturation limits might be 4.5 volts, something like that. You have to check the specs on each op amp, right? It's all different depending on what you use in your circuit. So let's go ahead. So VB, since we have an inverting kind of thing, let's go ahead and substitute in -5 volts. That's what our saturation will be. And yeah, I mean, let's go at it. So we have 1.6 over 0.25 times our 5 volts. Notice I've dropped the negative sign now. I had a negative on both sides. I just canceled those out. Minus the 12, all divided by 50. That would be equal to sigma. So I get something that says 0.4 is equal to sigma. So your saturation occurs when sigma is 0.4. Go ahead. I mean, we got an expression for VB. How about what is VB when sigma is equal to 0.272? You got it? Yeah, good. Of course, we can just plug this in. Yeah, and I got something VB is equal to -4 volts. Cool, huh? There we go. Last thing I'll just point out here, if we go back and look at VB. Okay, so let me, I guess I'll get rid of this little expression here. So the last thing I'll point out is if we look at VB, we could almost trace back the variables from which each of the terms came from, right? So right here we have the feedback resistor. So I guess I call that R feedback. I'll call it RFB. Okay? And then you have your current supply. Okay? So it's almost, I mean, you could say VB is equal to the potential over, for lack of a better term, I'll call this the parallel resistor times the feedback loop. And so again, you can kind of see where that amplification comes into play. Now notice this parallel, that's just the one that I use for the source transformation. It's like that other resistor going to ground just doesn't play a role in this portion. It's kind of cool. Yeah, ready for more? Hope you are. I just grabbed a couple. So here we go. How about this one? So you can also string op amps together. So you could imagine having like a cascading series of op amps to say amplify a number by 5 and then take that number and subtract it from another number. And so you could imagine doing this as a sequence of mathematical operations. So here again, I've just got some set of resistors and op amps, and the question is, can you find the output potentials? And notice those are in blue here on the right-hand side. Okay. So go ahead, take a minute, see if you can hack through it. You got it? Good. Hopefully you get a sense of, how to do these kind of node voltage and start going at it. I will notice that when here, instead of sometimes I've mentioned that if you have two lines that are intersecting and you don't want to have an electrical connection, you kind of do this loop-de-loop over them, one over the other. If you do want an electrical connection, usually what you do is you have two lines crossing, you have a dot. Okay? So no electrical connection, it'll just sometimes be two lines crossing without a dot, or I like it more explicitly having this loop going over. Okay. So that's why you see all these dots here, is they want to indicate that you have an electrical connection at each of those intersection points. Okay. So I'm going to go ahead and just for sake of argument, let's go ahead and I will do this in terms of variables. just so that we can get a feel for that as well. So I'll call this R1, R2, R3, R4, and R5. Now I realize that you probably already have your answer, and we can check the variable form and make sure that everything works out here. Okay, well, let's go ahead. So yeah, I have several junctions. I'll label them. I'm going to call this one node A. We'll have B here. Call this one C, and this one D as in dog. Okay. And we have our golden rules. So from the golden rules, we can immediately state that the potential at B is equal to, yeah, you got it, 15. And the potential at D is equal to 10. Good. Right? The inverting output matches the non-inverting output. Okay, so if I insert 15, this one's at 15. Okay. Now let's go through and let us apply our node voltage. Okay. Well, for A, I'll call it I1 going into op amp 1. So I'll call this upper one 1 and this bottom one 2. And what else do I have? I have VA minus 15 over 500. This goes against exactly what I said I was going to do. Excuse me. I'll call this VA minus V1. I said I was going to work in terms of variables, and then I started writing in my numbers. Sorry. This whole thing equals 0. Rigmarole equals 0. How about B? Well, we have V1 minus VA over R1 plus V1 minus VC over R2 plus V1 minus V2 over R5. And that whole rigmarole equals 0. Well, C as in cat. I'll call it I2 going into the second amplifier, second op amp. And then added to that, we have VC minus V1 over R2 plus VC minus V2 over R3. That whole rigmarole equals 0. And last but not least, we have our node D as in dog, where we have, okay, well, we have V2 minus VC over, excuse me, let's go up here to the upper, we're going to go up here to the upper corner because I've run out of space. So we have D as in dog. We have V2 minus VC over R3 plus V2 over R4 plus V2 minus V1 over R5. And that whole rigmarole equals 0. Hey, we've got everything we need. We can now find the output potentials, the two output potentials. Those would correspond to VC and VA in the variables that I have used. Okay. Now, yes, you could get an expression for the I's as well. We don't actually need those because we're not asked to find them. Okay. Well, let's go at it here. Sorry, I'm checking my notes. There we are. And we could sub and solve, or excuse me, we could do our matrix form and find everything at once. I'm going to go ahead and sub and solve because if we notice this bottom equation, this equation D, only has VC in it. Everything else we know, we're given in the problem. So we can find out what VC is right away. And then the third equation, highlighted here, once we know VC, we can find VA from this. So I've taken the liberty of rewriting the equation. And yeah, go. Let's solve for C. Right? So I'll just move VC to the other side. And you could probably already see this. We have V1, and I'll put 1 over R5, minus V2. And then we have all this rigmarole. 1 over R3 plus 1 over R4 plus 1 over R5. So at the end of the day, we get that V is some sort of scaled combination of V1 and V2. Ah, you should yell at me. I flip my signs. If I move this over to the other side, that means that V1 stays negative. There we go. Life has been restored. Well, there we go. If we actually go ahead and plug in now our values, okay, so the reason I did it in terms of variables is just so that we can kind of see what's playing a role, what doesn't. So you notice that R1, resistors R1 and R2 don't have any bearing whatsoever on the performance of the bottom op amp. Okay, it's just R3, R4, and R5. Okay? And if we go ahead and plug in all of our values, you should get VC is equal to 13.6 volts. Yes, I got a positive. Which also struck me as odd because we have stuff going to the inverting input. Yeah. It just struck me as odd. Anyway. So, okay. Well, if we have VC, you now notice that we can find VA. Okay. We go in and we plug in everything. I don't know if it's actually worth our time to see us doing that. Is it? Okay, you said it is. I can see somebody's nodding their head saying, yeah, it is. Okay, so let's see if I can, oh, excuse me. Oh, I went backwards, excuse me. Okay, so good, that means we have an extra page. So let's go ahead, we'll use this third equation here. Let me go ahead and write it down. Okay. All right then, and we have everything up and rolling. Let's go ahead, we find VA by itself, so there's only one term involving VA. So I'll go ahead and put it right here. And yeah, so I move that over to one side, so I got to be careful about my negative signs, otherwise I will just drop them. So 1 over R2 plus 1 over R5. And then we have something like minus V2 over R5 and a minus VC over R2. But now we go ahead and plug in our VC expression. Okay. So not to worry. And now we notice we have a double negative, right, for the first term. So I'll combine like terms in V1. And so we get something like V1, 1 plus R1 over R2 plus R1 over R5. And then R1 over R2, so we get a plus, right, so a double negative, R1, R3 over R2, R5. And then with V2, I'll put a minus V2. And then notice we have a minus sign and then a positive sign. So we keep the negative, okay? And we have something like R1 over R2, 1 plus R3 over R4, plus R3 over R5. And then we have this other term floating around here, R1 over R5. And we're done, right? So you can see that it's odd. Although C doesn't depend on resistor values R1 and R2, we see that A, VA, does depend on them. R3, R4, R5, all of those play a role. You have an R4 right here, though it looks messy. You have R5s. All the resistors play a role for determining the potential of A. Now, what I had when I went through and did everything, and this is kind of a cool thing, so keep in mind, I actually had 15.85. Yeah, what seems odd there? Yeah, hopefully you see it, right? In fact, I'm going to go and double check on LT Spice as well. But you see, this is interesting, is by stacking the op amps in this particular sort of arrangement, we've actually managed to get a higher output potential on one of the terminals. Okay. So the way I think about it, you say, well, how is that possible? Well, you have 15 volts from one of the op amps, but you have another 10 from the other one. And so this sets it up in a manner that allows you to get slightly higher than the output of a single op amp, right? If this were just a single op amp with a 15 plus or minus 15 volt supply, you would be limited to, 15. You'd have to be below 15 volts for the output. Here we see, because of how it's stacked and arranged, you can actually end up with slightly higher. Pretty cool. So let's take a crack at another problem. I've got it up here for you. You notice we've got two op amps with their outputs kind of going against each other. So go ahead, take a minute, see if you can hammer through this one. You got it? Good. So I'm going to go ahead, just like the last time, I'm going to go ahead and run this in terms of variables. And partially, this is with a thought towards that second question. If I have everything in terms of variables, then that second question will just simply be an application of the equation that I used to answer the first question. Okay? So I've gone ahead and labeled my resistors, and yeah, let's go at it. So the first thing I'm thinking of is, let's go ahead and apply our golden rule, and that allows us to say that the potential at A is equal to, excuse me, I forgot to label my nodes, A, B, C, and D. So the potential at A will be equal to, good, 0. And the potential at D will similarly be 0. Okay. So let's go ahead. Let's write down our node voltage expression for A. We have 0 minus V1 over R1. Okay. And then we have added to that, I'll put 0 minus VB over R2 equals 0. And let's go ahead. Similarly, let's write one down for D. Oh, actually, let's pause for a moment. You notice right away we can actually write down what VB is. Right, you see it? You get something like VB is equal to negative V1. And then we have the ratio R2 over R1. So it's just like our inverting amplifier. So imagine we're going to see the same thing for D, as in dog. Go 0 plus, notice that it's negative positive, right? So it's not a drop, it's a jump. And we have R4 plus 0 minus VC R2, or excuse me, R3. That whole rigmarole equals 0. And you notice again, we can solve for VC here. VC is going to be equal to V2, and we have R3 over R4. And we're done. Right? You see? And you say, wait a minute, Greg, what about the other two? Yeah, we could write down the other two node voltages, but those would be used to find the currents following into the op amps, the respective op amps. You notice right here, we're done. We can simply use this expression now. We have IA is the difference, the potential difference across the resistor divided by the resistor value, R5. So we're done. Let's go ahead and substitute in our values, but you have something that says the potential V2, R3 over R4, R5. And then you have a minus, so you have a plus V1, R2 over R1, R5. Well, yeah, let's go ahead. We can find out, let's answer the first question. What's the value of IA? So this first one, I get something like 0.1. Oh, excuse me, 1 milliamp. And what do we get for the other one? We get R2. So I get plus 0.0047. So at the end of the day, I have something like 5.7 milliamps is what I have. Boom. Done. Well, let's go ahead. We can answer the second question. You see that by having this expression, boom, highlight, in variable form, we can automatically answer the second question fairly quickly, right? So I've gone ahead and taken the liberty of rewriting the equation, and I've substituted in IA is equal to 0. So now we're just left with trying to find what the value of V1 is equal to. Well, we can do a little bit of razzle-dazzle rearranging. Right, R3 over R4, R5. And oh, goody, we see that there's a cancellation of the R5. And so at the end of the day, we have V1 is equal to negative V2, R1, R3, R2, R4. There's our answer. Of course, yes, you might say, well, let's get an actual answer. This is 150 millivolts. Let's see. R1 was something like 10 times 33 over, what was this, 47 times 220. Yep, looks good. All right. So now we're just in the situation. Let's go ahead. We got 330 divided by parenthesis 220 times 47. All right, times 150. So at the end of the day, I have something that says the V1 would have to be equal to negative 4.79 millivolts. in order for those two to match up. Cool. I'll circle that. Okay, well, I think that's it for right now. That's enough work. But we'll continue, just keep hacking away at those op amps. But I think it's time for us to start moving into the next section, which is going to be inductors and capacitors. So we're going to go back and revisit, see how we treat those when they're placed in a circuit. And then we'll start building up more complicated circuits using them. Hey, thanks for your attention. I'll see you next time.